Good evening, everyone. This is a session on Tuesday, October 21st of 2025 for starting with the lab 9. Lab 9 is actually last lab on the OPIS that we're gonna review it on OPIS 3 curriculum. And this is gonna be end of the radio astronomy class that we have. And by the next week, we're going to start hopefully with MWU, that is multi-wave universe for the colorful astrophotography. And that is going to be very interesting, I hope, for all of you guys. But this one, before starting, I give you some indication what we are doing. The last lab 7, we take some radio telescope from hydrogen emission on the 21 centimeter microwave wavelengths. And we get some information from Green Bank Observatory, and we did some radio observation. On the lab 8, we didn't have observation radio. We make it some kind of creating some graph for they get the expansion of the universe to see if it is accelerating or decelerating or constant. And we noticed that based on that measurement and hopefully based on your measurement, it shows that by a very simple tool, you can show how the universe is expanding and accelerating. And that's a kind of item that is professional astronomers they did it on last 100 years. And you can do it in a matter of the few days or few weeks. And with the tools that you have it on OPIS in the Skynet University. And that's actually, you can do it like a professional astronomer. You estimated those by the rubber band example that we have. And we show that how rubber band example, based on the lengths that we measure it, we can kind of model it like a wavelength and use it a simplistic tool to prove that the universe is expanding and accelerating. And here, the first thing on the law, Hubble law, that the Hubble law is basically based on the measuring the distance of the acceleration of the universe. And we showed some example like a balloon that is expanding. Every point on the balloon, if you attach some coin or some markup, if you're expanding and put it the braiding on the balloon and expand it, every point respect to each other, making a longer distance from each other. If it is originally 1 inch apart, then become 2 inch, 3 inch, and so. It doesn't matter where we look through it, every place is like that. Therefore, it doesn't mean that when we look through it on the universe, every point respect to other point is expanding. And we mentioned that on that expansion and the Big Bang, we have to consider that main concept. It is not explosion in the space. It is explosion of the space. It means that probably you hear near Halloween some fire or kind of explosions nearby, you hear it. It is kind of those, is we said, or you put some for a tradition, 4th of July or other Christmas time, you put some fireworks. Those is explosion in the space. But the Big Bang is explosion of its space itself. And we're gonna see how it's gonna work on the beginning on the lab 9. That is main concept that we learn. And another concept is that on the universe, we don't have a concept like a center or age. For example, if I have this writing pad in here, I know that we can define center somewhere here, and this is the age of it. But on the universe, we don't have that concept because we don't have any center and we don't have any age. And explosion happen on the explosion of the space itself happen. We're going to show how it looks like. Let me share you the material that we collected for this session. Hopefully you see it. This is you see the sky web assign curriculum?
Yes.
Okay, good. Then you click here on the 9 is a Hubble constant that we go on the next page. And here, typical to our labs, we're going to have some brief description about the numbers and the format that we're going to notation, seismic notation on the material of the submetal. And also here, the first school here is that idea title is Hubble constant, the expansion rate and age of the universe. That's the topic that we're going to look through it. The first, we're going to use the radio spectroscopy nearby spiral galaxies to measure their cosmological redshift. And then we use its Cepheid variables star. We're going to look through OPIS2 more detail on that, how we can use the distance of the different galaxy by using the variable star within them. And that is discovered by Henrietta Leavitt about more than 100 years ago. And her discovery is made Hubble able to discover the universe expanding and understanding of the galaxy. Before that, we didn't know there is a galaxy that consists of several million or billion stars in the universe. Therefore, this is going to be, or I will call it the discovery of the Henrietta that she made it about more than 100 years ago in 1908. It was a cornerstone of the modern astronomy as astrophysics. And without this discovery, we cannot understand the size of the universe and many different celestial objects like galaxy that is understood after that discovery. And based on that, we're going to, on the second item, measure the luminosity distance from us that we discovered the luminosity distance on the lab 8. And we're going to go over again on that. And then based on the number 1 and 2, we're combining this measurement to measure the expansion rate of the universe. And that is, we call it expansion rate of the universe that we convinced and proved on the lab 8. We're going to measure what is the constant, Hubble constant is, and we're going to do with a simplistic way to do that. And item 4 is use of the cosmic microwave background emission to measure Hubble constant in different ways. That's another way for the item 3. And item 5 also use your measurement of the Hubble space to estimate the age of the universe. Therefore, this is kind of end of the activity that we have on this lab that we're going to do. And whatever you needed is your computer and internet connection. And we go over the same things that we reviewed on lab 8. In here, for example, we said we reviewed together that very nearby galaxies like Andromeda are gravitationally bounded to Milky Way. We have several galaxies nearby. One of them is Andromeda. Do you know the other 2 or 3? Anybody guess? Nearby galaxies in addition of the Andromeda? There is a 2 very famous exists, but we cannot see it in Northern Hemisphere. It is on Southern Hemisphere. They call it the Small Magellanic Cloud and Large Magellanic Cloud. And the reason they call it cloud because in 1600 or after that, everything that they see it on the sky, they call it cloud. They didn't know that those are a set of the several million stars, galaxies. And galaxies are discovered in 1920s and after that. The concept of the galaxy wasn't known before 1920s and after Cepheid variable discovery of the Henrietta. And therefore, and Edwin Hubble make it this clear by his observation of using the Henrietta law. Here, many of the nearby galaxies like Andromeda, large Magellanic Cloud and the Small Magellanic Cloud gravitationally bounded to Milky Way. If we look through it, Andromeda is not going away from us, but coming toward us. And it probably in next 4 billion years, we're going to merge with the Andromeda galaxy. And you don't have to worry about that because it's going to happen about 4 billion years ago. By that time, probably Sun is going to be end of his life, and the life on the Earth not be have anymore. Nobody gonna exist on the Earth anymore. Therefore, this is kind of or item that we see it from current evaluation, except the Andromeda and the nearby galaxy that is bounded by our Milky Way galaxy. All others are exceeding for us. If we look through the diagram, Hubble diagram that we see it, whatever distance you have go farther down from ourselves, the apparent velocity of the residence is going to be more. If it is 400 megaparsec, the speed of the expansion and going away, it's going to be around 26,000 kilometer per second. And in here, in this nomogram, it shows on the other lab, we show it. This is a Big Bang explosion of the space. And the space is going to explode and become bigger and bigger and go on this diagram. It doesn't mean that the universe has this age, but this is kind of simplistic way diagram shows how the galaxy's motion on the space and space motion happen during the time. And this is X and Y we consider, this is time. This is a Big Bang, and this is now, for example. As you see it here, the galaxies are very close to each other, but the time is past, each galaxy compared to each other become more distance from each other. This is a very simplistic mathematical presentation of the Hubble law. You don't need it to memorize, but we needed to see conceptually how it is developed. And probably if you continue on the physics, you will get more insight on the mathematics and learning on that. But on this lab, we don't want to worry about that. We don't have to memorize it, but we can refer back to this lab material and keep it aside and memorize it. And like that is not needed on that concept. The parameter that we have here on the left side of the equality sign is a c times z. C is the speed of the light, that is constant, is about 300,000 kilometers per second. And Z is the cosmological redshift that we defined previously on the lab 7 and 8. And H0 here is, we call it constant Hubble's constant that we're going to measure on the lab. And DL also we defined on the previous, we call it luminosity distance. It means that the distance of the celestial object that we measure based on the luminosity and the graphs that we have as a standard calendar, like the Cepheid variables that we have. Let me show one quick time that we have on the lab 7, lab 6. Here. We're going to go on detail on the lab 6 on this matter, but let me show you if I have a graph. No, not this one. It might be on the other, yeah. And I think it's going to be on the lab. This time candles here. No, mistake. Standard candles. Yeah, here, as you see it, we have several graphs. This is variable stars that their luminosity is changing. But as you see it, the luminosity change is almost constant. It's not perfectly like this one that's showing here and here. They may have some deviation from the actual graph. But if we measure this period and this between the peaks, we can get kind of graphs on that. This is a graph that similarly Henrietta discovered. And if we know the, based on that, we can measure the luminosity and distance. And based on that, we can measure how much object is far away from us. But at here on the lab 9 that we are looking in this lab, is only we are looking to this concept as a kind of which parameter what they referring to. C is a speed, Z is a constant, H0 is constant, DL is also the distance based on the luminosity. The combination of the CZ is how fast they show that how fast the object is receding from us. C is a constant, but Z is everything as you see it on the previous lab is whatever is less than 1. In some occasion, you see Z value is more than 1. It could 1.2 or 3.3 sometime happen based on the different reason that we investigate on lab 7 and 8. But this CZ, it shows how the galaxy or celestial object is moving up fast from us. And therefore, this next one, luminosity distance, shows how far away from us the object is. Based on the graph that I showed a few minutes ago about the Henrietta discovery on the standard candles, that we see it on lab 5 and 6, we're gonna more detail a measurement on that on the OPIS2. And then based on if you just manipulate this equation, we can measure the Hubble constant H naught is equal to CZ divided by DL. Therefore, if we know the CZ and DL, we can measure the H naught. This is basic of our activity that we need to do on lab 9. And therefore, based on that, we can measure it how much this this item gonna move. But if you put the units of this one, this is a speed, this is constant, this is the distance, it's gonna be a speed unit based on the distance. If it is a speed unit, it's kilometer per second, and this one is a megaparsec is distance. And this is unusual unit because this is a constant that is created to make the law of the Hubble is popping. But this is just telling us how far fast we are going in kilometer per second on each megaparsec far away from each. It means that if you have 1 megaparsec far away one object, it's going to show combination of the Z going to show us how much the item gonna recede us and go away from us. And because of that, that is important to know and measure this item. On the lab 7, we measured the Z value for from the galaxy spectrum that we measured on the activities. And we can measure DL based on the activity that we have on standard candles on lab 5 and 6. That we don't need it to worry about that. At the moment, we're gonna learn on the lab 5 and 6 separately. Then on the next, so far, any question by the material? This is the main part of the mathematics that we have here to show how we're gonna do activity to measure the Hubble constant. Any question? Hearing none. And then this is one of the important part of it. Cosmic or measurement going to be based on the cosmic microwave background emission. And why it is we using that one? This one, Hubble constant, can be measured by very different methods. One of the methods that we're measuring is measuring based on the cosmic microwave background emission. And when the space is expanding, like here, space is exploded on the Big Bang. At some point in the past, everything was very close to each other. In here, assume very close to the Big Bang, it's very close to each other. When they are very close to each other, assuming this is a small combination that we have of the electron, positron, and the proton that we have on the beginning, on the Big Bang, they are very close to each other. Therefore, they cancel each other when the microwave emission comes, because they are very close to each other, very dense. Therefore, we cannot see anything come out of this combination of the dense material on the back very close to the Big Bang. But sometimes when they are receding from each other, for example, in here, you see the electron and protons become far away from each other, a hydrogen atom is created. And that time, we were able to see it. This is the area, we call it recombination. It means that if we look through back, there was everything was very close together, then so close together that would not have distinct galaxy or star. Nothing was there. And instead, everything would have been mixed together, a dense hot gas or plasma, whatever we see it. If we go back far enough, this gas would be so dense that can be kind of opaque or dark, that meaning that neither radiation can emit anything due to the temperature. We call it this one black body radiation that would be immediately reabsorbed by the different particles or object that is nearby. This is very important concept that is we know on the cosmology that after about 380,000 years after the Big Bang, the universe become expanded enough like here, the nomogram that you see it here, the density of the gas was dropped a little bit compared to this on the left. And therefore, at this point, black body radiation would no longer be reabsorbed by particles beside on this dense gas. And therefore, from this point in space and in every direction, we see the universe. Therefore, probably somewhere here that is kind of very close to the Big Bang, we can measure it. This is one of the activities that James W. Webb, that is a few years ago, descended to universe, is expanded to the space to measure very close area to 380,000 years after the Big Bang to see if we can see anything here in mostly on infrared mission. And because of that, they put it backside of the Earth far away from the sun to make sure that we measure that area that might be very active on infrared radiation. And technically, this density drops, temperature drops, the gas transmission happen. We call it a specific, this is a astrophysical and cosmological term. We call it recombination. Why they call it recombination? Nobody knows, but probably it is because we created some atoms together and decoupled, black bond radiation decouples from the matter, and we can see the universe. And this is a little bit background history in that that cosmological redshift that we see it on Lab 7, based on the microwave and radio wavelengths, that helped us to get more knowledge on the universe and expansion and prove the Hubble law. And this guy that you see it here is the one that is, Arno Penzias and Robert Wilson in 1964. They discovered CMB, cosmic microwave background emission. And therefore, by accident happened. They working on the Bell astrograph company right now. They producing the radio signals for the communication, and they was engineer over there. And then by accident, they found that a horn on antenna of the radio wavelengths that they're using for the communication towers. And by the 1992, it means from, you see, 1964, about 30 years, NASA cosmic background Kobe spacecraft confirmed also that there is a two confirmation we have for CMB, one by the accident discovery by these two guys on 1964, and then later on by Kobe spacecraft NASA in 1992. If we look through the graph that we discovered, radiation is almost perfectly uniform across the sky, almost. It means that doesn't matter on which direction you look through it, the uniform, this radiation is uniform. And this is very important. And as you see it here, this shows the cosmic microwave background spectrum. And this is the Kobe diagram and black body spectrum that is observed, and it shows that match exactly with each other. After 380 years that we say that the universe become observable, the dark matter in universe should be began to clump under influence of the gravity, but only one part of the in 100,000. It means that very less amount of the value. And this create a kind of very concept. I'm emphasizing this because this is very important that we know the cosmology in this sense that how we get to this point that we have. This should one part on 100,000, 1/100,000 is very low temperature variation as due to the, you see that is very low. 1/100,000 is very small number. And this is another key prediction that is Big Bang theory, which was confirmed by spacecraft Kobe and NASA, another mission, Wilkinson probe, we call it WMP in 2003. Also, all of them, they convinced that in 2013, this all the measure that you see it on this nomogram, this is a picture of the universe in the Kobe WMP and the Planck. As you see it, we come here, we get more uniform distribution of the CMB on the universe. This is our universe baby picture, and when it is about 380,000 years old. Before this, the gas was thick and no light escape from condense and dense material that we have. And this is very important. We said we call it this event that happened, recombination. And why does dark matter clump but normal matter does not? This is one question that you may ask. Why it is dark matter clump but normal matter does not? The normal matter is too hot to clump. The reason is that the answer is here. Normal matter is very, because of that we call it normal matter and dark matter. Dark matter is very cold, and dark matter cannot absorb the normal matter background radiation, and that is help us to get more distribution better than the visual observation. And that's the way that radio telescope help us, as we mentioned on the lab 7. Okay, going back to this important item that we're gonna consider in here, clumping occurs on all scales, but on one scale is favorite. This scale is set by how far pressure waves could travel in universe the first 380 years, the maximum distance over which gas could push around. We call it this one radius R. Radius R is related to the first universe 380 years on the universe. And this angle that the clumps happen for the dark matter, we call it by kind of angle of theta. We're gonna see what that means. And it is proportional to R over D. And you don't need to memorize those again, but only you need to absorb the concept. What is the theta and what is R and D? I'm gonna describe it. Hopefully we get the point what we're reading. R is, we said, distance. The constant is distance is clear. And D is here, according to the Hubble law, D is equal CZ over H. Why? We go back here. If D here, if we're going to calculate D is equal CZ over HO. You divided both sides for HO, and you can get D from this one. Therefore, if we get HO calculated on the first step, we can get D. And if we can get D, and we know the R, we can get the angle of the clump on the universe. And that's going to help us to understand what the early universe, nearby universe, not what is working and how we can measure it, D and the other parameters. And again, you see it, D is here proportional or inverse of the 1 over HO. The key thing is that if we can measure HO, we can understand many other things that we see it on this picture. This picture is going to be basic of the MWU that we're going to see later on. As you see it here, HO, as if HO is larger, Day is smaller. Why it is like that? Because on here, if you see H become larger, 1 over H become smaller. Therefore, when H is become larger, D is become smaller. What that means? It means that CMA is close to us. It means that CMB is going to be very close to us if it is this happen. And consequently, the R size clump will appear bigger. And why it is appear bigger? Because this is very close to each other, and this is constant, and that is reverse. And therefore, if H is smaller, reverse going to happen. D is larger, means that CMA is farther from us. It means that we're measuring the cosmic wavelength that is very far from us. And consequently, air size clumps will be smaller. And therefore, we can see on the following section. As you see it in picture, this picture shows very good to make sense whatever we said so far. As you see in the picture A on the left, if H no were larger, the same as you see it here, this is a color we assign it for different topics that we have. As you see HO larger, we show it with the red color. CMA would be closer to us, so the clumps would appear bigger. And if is how big the clumps in the CM actually appear. Sometimes you see clumps are different on different region. If HO were very smaller, the CM would be farther from us. Therefore, if you see the farther distance object, you don't see that much clump together, but clumps going to be distributed and very small. As you see the picture here, this will show very accurately how that concept we measure by the evaluation of the picture. Consequently, theta is proportional to H0, and therefore, based on that, H node also proportional to theta. With having one of them, we can trigger the other and understand each other. This formula, we're going to use it based on the approximation that we have on this equation, that this is the formula that we're going to use on this concept, how the H node related to theta on our measurements. And here, it's going to show another tools that we're going to measure it here. By the Hubble constant, we're going to use the same formula. When we're measuring the distance, we're measuring exactly what is given in here. Similar way that we measure on the lab 5, 7, and 8 for the distance and expansion of the universe. We just make a trick to dissipate, for example, some of the parameters. And what we do, we actually we consider its unit again. Unit is kilometer per second speed over distance. So it is measuring the rate of the speed over the distance of space. Since beginning of the time, m parsec has expanded exactly 1 megaparsec. It is in the beginning of the time. We are assuming that is the expansion happened on 1 megaparsec. Therefore, on average, therefore, we're going to have a rate of this based on our measurement of the distance, 1 megaparsec per time. And the time is age of the universe. And this is proven and based on the observational professional astronomer tools with different methods. And it created this formula that we have here. The T is the age of the universe, hence the Hubble constant must be given by this formula. Therefore, this is the speed. Again, instead of the kilometer per second, we just writing 1 megaparsec by T, and here is 1 megaparsec. The same thing that we have in here. As we see at the units, where was the unit we showed here earlier? Yeah, here, the unit we had. And when we just cancel out the megaparsec, we're going to be 1 over T prime. And this one, P is proportional with proportional to 1 over H naught. And therefore, this is way that we're going to measure the universe. If we're going to say some pictures on that, it goes better understanding. As you see it in most of the picture, we show it, this is Big Bang explosion of the universe. Why we didn't draw somewhere here and here? We're assuming everything is happening on this direction. Why it is on direction? Because we just thinking kind of concept that is based on our understanding of the physics law. Because if it is something happen here, it means that it has to be speed of this object going to be more than the speed of the light. But we know that the speed of the light is constant. And because of this angle that you see it about 45 degree, it shows that a maximum speed of the light. Light or not anyone can go beyond the speed of the light based on the special theory of the Einstein. Therefore, we show it like this, and it's sort of like a expanding horn in this consideration. We call it different numbers here. This is we call it quantum fluctuation, inflation. Those are cosmological terms that if you're interested, you will learn later on. And this is, we call it Big Bang expansion. Here, we are at this moment on this location. That it shows graphically how this gonna be present. Therefore, this is a very basic tools of the question that we have. And the next thing that we're gonna do, some radio observation. Before I continue, I just stop here to see how you are and if you have a question on this very historical and topic that you have. Go ahead. Go on.
Professor, how can there be a distance between us and the cosmic microwave background? Isn't the CMB sort of like everywhere?
Yeah, it is as I showed that globe picture. If we see every direction, for every direction we see CMB. You see the picture, colorful picture, you see it? It shows that we're receiving CMB from every direction. It doesn't matter, it comes, because if it is come from one location, that's totally different. But based on the measurement that is done from 1965, 1992, 2003, and 2013, we show it on different historical measurement on the different devices. We see every direction we look through it, we see same CMW. But in some areas, they are uniformly overall. If you look through that measure, let me show you again this graph. It might be show it better for you to answer the question. Here, as you see it here, you see most of the area. Although you may see it, some area is blue, some area red, but only consider the one that is red in this picture. And similarly on here, as you see it, the distribution is almost similar if you look through all of them in different colors. But the distribution, it doesn't mean that all of them is concentrated here or all of them concentrated here. You may see it, there is some variation, blue and red. But those are not our concern. My point is that if we look through here, we have a CMW, same clumping, same clumping, same clumping, same clumping, here and here and here, everywhere is almost similar. It means that this is similar to each other. Then for the distance, we look through here. For example, this one, clumping is here is bigger. Therefore, we can see it, the CMW that we're receiving the wave is here is closer, but here is you see it very smaller. Therefore, these are the more distance object. Here in the middle we have. But let me go over the show you another thing. I think this one may describe you better on the lab. I think let me see, lab 7. We had on here material we showed here. Let's see, not here. Oh, yeah. No. Might be on the lab I went to lab 8, I think. We just show it over there. There is a graph that shows the balloon and the waves that we have. Let me see here. Let me see. No, it's not here. Let's see again. 7. No. That picture that I'm going to show you. It show how the system works and how we get that point into consideration. Let me see again. Here, no. I think it might be on the beginning chapter part of the section, not first. Yeah, here. Yeah, here. Oh, yeah, here. You see, then when we have this balloon expanding, the wave is not the matter. We have two concepts on the physics that are slightly different than each other. Sometimes you heard that particle and wave. Matter, sometimes the physical parameter can be defined as a kind of a particle, like a photon. We consider the light as a emission of the photon, a small particle of the light. And sometimes you can measure it like a wave, like this one. When the space is expanding, the waves are also stretching. Therefore, you see it in here, this become red shifted. And therefore, based on the concept that we learn here on the 9 item that we had it here, on this subject, therefore, this red is identifying that red shifted CMBs. And because of that, that is a smaller clump that you see it on here on the picture. It shows that this object is far away. But it means that the wave is coming constantly for us. It doesn't mean that wave, like if we assume wave that on the lake, if you drop some stone on the wave, on the lake, it's going to create a wave of the water on the lake or pond. That is totally different than the wave that we see. Wave is almost can go any place on the universe. Therefore, it means that this comes from the far away, and we see it constantly. This is happening, and but is not accumulated in one part like this one. And because of that, we call it this one is more distance, and this one far distance. This is very close to us based on the logic that we define it here. I hope I catch your question correctly. If I'm not, let me know.
Okay, that makes some more sense. Thank you.
You're welcome. That's the kind of things that when we say it, if you take the rubber band, make it kind of wave like this, it's not like a wave. Is we cannot say it. One of the key concepts that is on the wave that is very important. Let me show you some example that gives. This is the very basics of the physics you may learn when you go on the physics items. Let me see if I can find it. I'm gonna find a small sphere. I have to put that sphere beside my that's it. For sure. Assume a small sphere that you have it in your hand, very small sphere like in your consideration. This is, you can define it by a point. This point is going this way and that way in direction. That point, the location on the spaces, the universe is fixed. And that is, we can define a coordinate. For example, you say at the level left of my room is the origin of the coordinate. You put X and Y and Z, like the one here. Let me show you again. In this example, you say, I can put a point here, this point, at this point, this point. Each of them compared to this coordinate is very clear. But when you are talking about the wavelength, wave is different. Wave doesn't have a point. Wave have wavelength and also frequency. It means that if you see the light here it comes from the light bulb on up in your room, it comes scattered all around the direction. It means that if you are here, you see it. That CMW is also same thing. It is kind of emission, electromagnetic emission. It goes on every direction. One of the key things that is defined in the physics is we call it field. Field is the means that if the emission gonna happen on this from this source, it's gonna be field. It's gonna be detected here, detected here, detected here, detected here, detected here. It doesn't have any coordinate. It goes everywhere regardless of the location. Therefore, because of that, CMW can be observed on everywhere from our universe, on every direction. And because of that, we can understand the universe better.
How is the distance to the CMB measured?
How they measured, that's the one that we're gonna look over on this lab 9. And also we're gonna we did some on the lab 7, but we're gonna different way in here. I'm gonna show quickly, but we're gonna go on deep on the next session that we're gonna go to the measurement. Let me show it to you here. In here, we're gonna go to the observation. Therefore, we're gonna go Skynet. Do you see my Skynet picture on the screen?
Yes. Yeah.
Okay, yeah. Then here you go to the radio observation. And here for the radio observation, you're gonna do the add new observation. When you add new observation, there is a many item that is identified in your class. For example, if you go down to lab 9, we have several items we provided here: NGC 253, M74, M82, and NG. You don't need it to do all of them, but these are the target that we're gonna use, and we call it on and off procedure. And we're gonna see how we can do that. And also there is a tutorial here exists in both of them. You can go and check it based on the item that is. This is very simple to look through it. The reason is that, for example, the basic of the picture is like that. When you assume a galaxy nearby, this one is coming toward us and this one going away from us. It is rotating around the center, like a solar system, assuming. Here, therefore, it's going to be blue shifted, here going to be red shifted, and here going to be shifted on the center. Therefore, this is a Milky Way 21, what do you call it, centimeter emission measure. And we're going to check it, how we're going to see it on the next week. But that's going to be, we call it 21 centimeter spectroscopy. That is very cool too. And we can use it any of them or something else. Let me do what we should do at this moment. Go to the Skynet. We just put here M82. M82 is this one. Let me see, cigar galaxy. And then you go M82 search. If you look through search, it brings the coordinate and location on the, location on the here. You see M82 is here. And you have to look through to see how much far away from the sun is. As you see it, the sun is always provided by yellow dot here. You see the sun is here and this one is here. You have to have at least 10 degrees or more. I prefer more than 10, but at least minimum 10. Therefore, you have to make sure you name it here. For example, Messier 8, or 81, or I will call it M, to make it shorter, M82, lab 9, high initials, or date, for example, October 2025, something like that. And then we said minimum, this is very important, minimum separation going to be 10. Why make it 10? Because we're going to do the radio observatory based on the, let me see, the 7. Whatever we're going to do, equipment, based on the Doppler effect that we see it on the Green Bank Observatory. On the Green Bank Observatory here, if the sun is very closer to the object, therefore sun gonna impact this dish and the sun gonna be reflected. Sun is very active radio source. That's gonna impact our measurement. Therefore, because of that, we just make it 10 degrees away from the sun, but more is better. For example, in here, as you see it, M82 and sun is very far away. That's better. You can check it something else, M83, for example. Check M83 here. You see, M83 is might be enlarged here, very close to each other. Each line here is the 10 degree, and 10 degree here, 10 degree here. Therefore, the distance between sun and the M83 is also around 20 degree. It's still good, but from my point of view, if you look to M82, and let me zoom it out. You see, this is far away. This one is better choice for this consideration. As you see it, this is 15 degree. And also another important that you have to have at least 15 degree far away from the elevation. As you see it here, most of the M82 always is above the green bank, above the horizon. And that's good choice. And then here, on this second option, you're gonna choose the high resolution mode. And this two frequency of the H-alpha is a center frequency and secondary is normally we're using. This is 1024 also channel. We're going to use the same. We don't change, only the one that is going to change it here, high resolution, save and continue. Here, previously on lab 7, we used track. But here, we're going to use different method, on and off. And we're going to see how that on and off working. But briefly speaking, we describe it here that we're going to make it on and off to make a measurement of the different spectrum and to find out the how much distance receding object together. Here, for example, whatever credit that we have, we can choose it here. Duration that we're going to use here is 60 seconds, and offset is 2 right ascension, and here we're gonna set offset on degrees is about 10 degrees. Let me see if it is correct before I made a mistake. It's everything is given here on the. You see this one is correct, high resolution. Here is 60. Oh no, 0. It has to be 0. 60 to 0. Therefore, here you come back 60 to 0. And this is the offset from right ascension, offset from declination. And this is kind of item that we using degree offset for the measurement. And why this is value given? This is based on the professional astronomers' recommendation. We're using this one. And then total estimated observation time will be 2 minutes. It means 120 credit. And save and continue. And here you just make sure that you check your data. If the observation name is not the one you needed, you have to go back and change it. Make sure everything is high resolution and the frequency and everything is correct. On and off path type that we have on and off. 2 degree offset on azimuth on the coordinate, on the other one 0. Duration 60 seconds. Integration time 0.3 and repeat 0. And you're going to submit 100 degree and then submit. And therefore, you're going to complete this task like that. I have another example that I did it before, this one. I will show it to you. This is a picture that they show it here. Therefore, it's going to be very gigantic in this kind of item that shows here. And we're going to look through it more closely in here based on the different item that we have. This is a calibrated spectrum on position. And we go back. And this is the calibrated off position. And we're going to see each of them, what they tell us. And we're going to use the live spectrum here to get some measurements on the kind of Hubble constant as needed. But we're gonna go through it more detail on this. This is gonna show you how it's gonna work. But basically, this is a observation that you're gonna make it as I describe it on the lab 9. The data is provided here. Either of them is, you can choose it as you need it. And then on the next procedure, next week, we're gonna go over to which one of them. And this is gonna be take about 120 credit from you of your 1800 credit. But please make sure that you do it diligently, double check before submitting to make sure that you don't lose 120 credits. Any question? Okay, hope you are successful on the submission, and we'll see you next week. If you have a question, let us know by email or chat. Have a good night.